Hello everyone, welcome to a new video in a series of videos about statistics. In this series of videos we were looking at more advanced types of analyses, and in the prior two videos we were talking specifically about linear regression, in which we related some kind of independent variable to a quantitative, continuous, dependent variable. In our case that was BMI and blood pressure. But in this video we are going to talk about if we have maybe a different type of outcome variable. For instance, a dichotomized variable, a variable that can only take two values. In that case, we have to use a different type of analysis, and that is called logistic regression. So in this video, we will talk about an introduction of logistic regression. So first, let's do a quick recap on what we learned last time. So in the last video, what we did was discussing linear regression. And what we did with linear regression was we wanted to analyze some kind of relationship between two variables. In our case, that was BMI and blood pressure, the blood pressure being the dependent variable. And we did that by fitting a straight line through the data points by assuring that the squared distance from the line to each data point was minimized so that the line fits the data the best. And we did that by some technique called ordinary least squares, or OLS. But what if our variable is not a quantitative one? So not blood pressure, but for instance, a dichotomized variable, for instance, indicating low to normal or high blood pressure. In that case, linear regression is not usable, and I'll show you why. So let's take a new example. So in our new example, we will not use the quantitative dependent variable blood pressure, but a dichotomized version of it. In this case, a dichotomized variable can only take two values. In our case, 0, indicating a low to normal blood pressure, or 1, indicating a high blood pressure. Similar to our last example, we will try to establish a relationship between the association of blood pressure and BMI. But in this case, blood pressure is not quantitative anymore, but a dichotomized variable. And here we have our data. Once again, there are very few data points, a little more than last time. But what we can see is that we have 10 observations, each with a status, so indicating whether somebody has a low to normal or a high blood pressure, either indicated by a 0 or 1. And on the very right-hand side, we have the respective BMIs of each of these observations. So we can see the first observation has a BMI of 18, second one 21, etc., etc. So we could approach this with a linear regression. However, actually, that's not really possible because, crudely speaking, a dichotomous variable is not normally distributed, and therefore we cannot really use it as the outcome of a linear regression. As an alternative, what we can do is we can try, instead of actually modeling the outcome, we can try to model the probability on the outcome. So the probability of some outcome, either 0 or 1. However, if we do that, which I can illustrate. So let's, for instance, take that approach and use the dichotomized version, or the probability of blood pressure, as the outcome of a linear model. So as normal, we have an intercept and we have a regression coefficient times some kind of independent variable, which in this case is BMI. What you'll see is that for very low and high values of, in this case, BMI, we will violate the rule of probability, which indicates that a probability always lies between 0 and 1. In this case, what I did is using a linear regression approach. So I actually, by using ordinary least squares, I determined some kind of linear model, which was equal to minus 2.036 plus 0.101. And when I calculated using this regression equation, the estimated high blood pressure, the estimated probability on high blood pressure, I got a value that exceeded this probability domain. Namely, I got a value of minus 0.218. And negative probabilities in the basic principles of probability don't exist. And the same thing holds for when I used a very high value for BMI, 35. I got a probability that exceeded 1, which is also not possible. And this also becomes evident when you look at the scatter plot. So here I made a scatter plot with, on the y-axis, the outcome variable, which can either take a 0 or a 1. That's why it looks a bit strange in this case. And on the x-axis, we have BMI. And when I draw a straight line through that, you can see that if we were to calculate beyond the BMIs that we observed, we estimate probabilities that violate this rule, this probability rule. So although this doesn't work in the sense of linear regression, this is what we will be doing with logistic regression. What we will be doing is we will be modeling the probability that some outcome occurs, given some parameters. But how we do that, we will discuss now. So this way it doesn't work. So what do we have to do? Well, what we need is we need to find some function that allows us to stay within the domain of probability so that the rule holds that a probability always falls between 0 and 1. However, we want to model it in such a way that the outcome of our regression equation can take values from -infinity all the way up to infinity, and that we can approximate linearly. So the first step that we can take to get there is we can transform our probability to odds. And odds, if you are familiar with those, can take values ranging from 0 to infinity. So that's one step ahead out of that domain of probabilities. So first of all, to calculate the odds, what we can do is we can take the probability of some outcome, in this case high blood pressure, and divide it by 1 minus the probability of that same outcome. The next thing that we can do is we can take those odds that we just calculated and take the natural log of those, resulting in the ln odds or the log odds. These log odds can actually take values ranging from -infinity all the way up to infinity, and it can serve as the outcome of our linear model. So what we end up with is we have some regression equation that predicts or that calculates the log odds on some outcome. And if we can calculate that log odds, we can also transform it back to a probability. I'll show you how that works in a second. Since we want to estimate the probability, because we don't know the probability, we invert the formula. So what we can do is we can say that probability equals the e to the power of the regression equation divided by 1 plus e to the power of the regression equation. I will get back to this formula in a second, and then it will hopefully start to make a little bit more sense. But what I want you to see here is that what we did is we related some quantitative outcome as the outcome of our linear model, and we linked it to the probability without violating the rule of probability. And you can see that when we graph those things in this graph right here. So on the y-axis we have the probability, and on the x-axis we have the log odds. And what you can see is that the line never hits the 0, and it also never hits the 1. So it stays within that domain of probability, while we still have an outcome that can take on any value between minus and plus infinity. So this link that I just talked about is what we call the logit link, and it provides us with a way of still approximating something with a linear function, even though our variable is dichotomized. And so we have solved our problem. So before we get into how we determine our model, because last time that's what we started with, in this case we're not going to start with the estimation of the model, but we're going to start with what the results of a logistic regression looks like. So in this case, I have already provided you with the equation that best fits our data. How we come to that equation we'll get in a minute. But first, let's look at how we interpret this model. So the log odds on high blood pressure is equal to -30.42, which is the intercept, plus 1.204, which is the regression slope, times BMI. The good thing is that most of this interprets exactly in the same way as we saw with linear regression. So for instance, the intercept of the regression equation indicates the estimated value for the dependent variable when the independent variable is equal to 0. So in this case, what that means is that the estimated log odds for high blood pressure when BMI equals 0 is -30.42. Subsequently, the regression coefficient gives us the estimated difference in the dependent variable when the independent variable increases with 1 unit. So in our case, if BMI increases with 1 unit, the estimated log odds for high blood pressure increases with 1.204. Now, since we have this regression equation, we can also make specific estimations. So for instance, we can calculate the estimated log odds for high blood pressure for a person with a BMI of 26. What we can do is we can just plug in the numbers, minus 30.42 plus 1.04 times 26, which was the BMI, equals 0.884. So that is the estimated log odds on high blood pressure for a person with a BMI of 26. But what does this figure really tell us? What are these log odds? How do we interpret these? This is not very informative. Well, we have a solution for that. Because remember, we took the natural logarithm of the odds. We can also exponentiate the natural log to get back to the odds scale, which are easier to interpret. So what we usually do is when we calculate some outcome with a logistic regression, we then exponentiate those values to get back to the original scale, which was the odds scale. And we can interpret those values in terms of odds or odds ratios, and I'll get to that in a minute. So let's do that for the predicted value of 0.884. So when we take e to the power of 0.884, that equals 2.42. Now, odds I won't get too deeply into, but they are similar to probabilities, although a little bit less intuitive to interpret than probabilities. But in principle, an odds of 1 means that either outcome is equally likely, so a probability of 0.5. In our case, what we found was that the odds for high blood pressure for somebody with a BMI of 26 is 2.42. So what that tells us is that it's much more likely than not for somebody with a BMI of 26 to have high blood pressure. In the case that this value would be below 1, so for instance 0.5, in that case, it would mean that it was less likely to happen for a person with a BMI of 26 to have high blood pressure. So that is how you can interpret odds. This is already a lot more informative than those log odds that we saw earlier. Now, additionally, we can apply that same transformation to directly transform coefficients from the regression equation to a more meaningful interpretation. Now, this is most often done for the regression slope, so beta 1. So as we saw earlier, in the regression equation, we saw that the regression slope had a slope of 1.204. So we can exponentiate that value and we arrive at the value of 3.335. Now, what does that indicate? Well, remember, the regression coefficient indicated an estimated difference in log odds. So if we exponentiate that value, we are now left with an odds ratio. And the reason for that is that when we take the natural log of something, we transform it to an additive scale, whereas when we exponentiate it back to its original scale, we bring it back to a multiplicative scale. So in this case, what does that mean? That means that the estimated odds on high blood pressure are 3.335 times greater for each unit increase in BMI. So it's no longer an additive interpretation, but it's a multiplicative interpretation. Now, let's move on to another important aspect of logistic regression, because these odds, like I said, are not often the most intuitive to interpret, and they don't serve as the final outcome of our logistic regression. It's all based on the probabilities of the outcome. Well, like I said, we can transform odds to probabilities, and this step will also let that regression equation we saw earlier make sense. So let's transform the odds that we estimated earlier, the 2.42, to a probability. We can calculate the probability by taking the odds and dividing it by 1 plus the odds. So in our case, that is 2.42 divided by 1 plus 2.42, and that equals 0.71. And remember that I said with an odds of 2.42, it was more likely than not for somebody with a BMI of 26 to have a high blood pressure. And we can see that because the estimated probability is 71%. And that's higher than 50%. Now, we can take that back to what we saw earlier with that regression equation when I was explaining the logit link. You can see that we can just write this formula differently by estimating the probability directly by just taking e to the power of the regression equation, because remember, the regression equation in principle estimates the log odds. And when we exponentiate the log odds, we get the odds. So e to the power of the regression equation is just the odds. And because the probability is equal to the odds divided by 1 plus the odds, we can just write 1 plus e to the power of the regression equation. And we are left with directly estimating the probability using the regression equation. Okay, now let's go back to estimating the model, because how do we get to that model that we saw? So we had this model minus 30.42 plus 1.204 times BMI, but how do we get that model? So the estimation of a logistic model is somewhat similar to linear regression in the sense that we try to find a model that fits the data the best, but the way that we approach that is a bit differently. Now remember, with logistic regression, we were estimating probabilities. So what we do with logistic regression is we accomplish the estimation of this model by choosing the values for the regression equation in such a way that the product of all the probabilities that it estimates is maximized. So in that case, the model would have the highest likelihood. And we do that in certain steps. The first step is that we try out different values for the regression equation. We do that iteratively. So we keep just using new values and we estimate probabilities. The second step is that based on those values, we estimate the probabilities for the observed status of an observation. And I'll show you how this works in a second. And we multiply all of those probabilities with one another to get one final probability. And then finally, we choose the values for the regression equation in such a way that that probability is maximized, which makes the model the most likely. And to no surprise, we call that maximum likelihood estimation. So we choose the values for the regression equation in such a way that the probability of the model is maximized. So let's see how that looks in action. So we have our data. Let's just try some values for the regression equation. For instance, this one right here. The log odds on high blood pressure is equal to minus 10 plus 0.4 times BMI. Well, what we can do is for each observation, we can just determine what the predicted probabilities are. So in this case, for the first observation, we see that the status of that person is 0, so low to normal blood pressure. So to calculate the probability on that status, we have to estimate the probability on high blood pressure and subtract it from 1, because remember the complement of a probability is 1 minus the probability of that outcome. So we can simply do that by saying 1 minus e to the power of minus 10 plus 0.4 times 18, which is the BMI, over 1 plus e to the power of minus 10 plus 0.4 times 18, which in this case equals a predicted probability of 0.94. Now we keep repeating this process for each observation. Once again, we keep looking at their status and we estimate the probability on that status. So for the second probability, for the second observation, we also estimate the probability of having that low to normal blood pressure. And apparently, in this case, that is 0.83. Now, I won't do that for every single probability because you get the point. We do this for each and every single observation. Remember that when we encounter somebody with a high blood pressure, we of course don't use the 1 minus anymore, because then we are just estimating the probability on high blood pressure. For observation 9, it's 83%. And for observation 10, it's 92%. So here you can see in this column right here, we have all the predicted probabilities. And the next step that we take is we multiply all of these probabilities with one another to get one final product probability. And in this case, that is 0.025, so 2.5%. That is the performance of this model. And when we plot that in a logistic curve, we can see it looks somewhat like that S-curve we saw earlier, but it doesn't fit the data as tightly. So what we can probably do a little better than that. So let's try another equation. For instance, minus 17 plus 0.7 times BMI. We just repeat this whole process. So we estimate all the probabilities of each observation. So in this case, observation 1 now has a probability of 99%, observation 2 has a probability of 91%, etc., etc. And we have all the predicted probabilities and we multiply them by one another. And in this case, we see that the product probability now is 0.04. So it has increased. The model has become more likely, 4%. And we can see that the curve now fits the data more tightly. You can see that more probabilities are now around the 1 and the 0. Now, I won't do this over and over again. You get the idea. We try to find the model in such a way that those probabilities are maximized, maximizing the likelihood. We keep repeating that process until we maximize the likelihood function. Of course, in practice, we don't do this by hand, but because this is a lot of work and it's just not necessary. And we have a smart algorithm to help us with that. The algorithm solves the equation for us in such a way that it maximizes that likelihood function. And in this case, that means that our regression equation will result in what we saw earlier, minus 30.42 plus 1.204 times BMI. And the likelihood function of that equation is 0.066. That is the maximized likelihood belonging to this equation. And it results in the following S-curve. And you can see that it fits the data even tighter than we saw earlier. Now, with this overly simplified model, we saw that that product probability, 6.6%, 0.66, was already fairly small. Not that small, but you can probably see that when you have 100 observations, for instance, this figure can get very, very, very tiny. That is why in practice, we don't actually use that product probability anymore, but we use the -2 log of that product probability. And that is also known as the -2 log likelihood. We can use that quantity to determine if our model is statistically better at explaining the dependent variable compared to another model, or for instance, an empty model, just like we did with linear regression. So it's a bit different in terms of explaining variance. In this case, we look at how much better does it predict probabilities when we compare it to a model that doesn't have any variables or a different set of variables in it. And we do that by comparing the -2 log likelihoods of each model. So we take the -2 log that we just saw, and we take the -2 log of another model, and we compare the two. Well, to do that, we have to, of course, calculate the respective likelihoods. So we already determined that the likelihood of the model that we saw earlier was 0.066, and we arrived at that figure by multiplying all of the predicted probabilities of each observation. So once again, in red, we have the probabilities for low to normal blood pressure, and in green we have the ones that for high blood pressure, and we arrived at 0.066 as our likelihood function. To get the -2 log likelihood, we just take the log of 0.066 and multiply it by -2, and it gives us the -2 log likelihood. In this case, it's a figure that is 5.425. Now, it may be worth noting that we actually don't try to maximize the likelihood, the -2 log likelihood, but we try to minimize it, because if the probability were to be 1, the -2 log likelihood would be 0. So the lower the log likelihood is, the better the model is. Now, the same thing we have to do for an empty model. So let's say that we would want to compare this model to a model in which we did not use BMI. How much better does BMI predict the high blood pressure compared to a model in which we have no variables? Well, we would have to calculate the -2 log likelihood for an empty model. So in that case, that would be the -2 log likelihood for a model if the null hypothesis were true. In other words, if there was no relationship between BMI and blood pressure. So how do we calculate that? Well, we just look at how much the outcome occurs in our data. And in our case, we saw that 5 people had high blood pressure and 5 people did not, indicating that if we didn't look at any other data, we would estimate that the probability on the outcome would be 50%, because it's equally likely, it occurs equally as much in our data. So what do? Well, the probability on the outcome is 0.5, so the probability on low to normal blood pressure is also 0.5. So that is 0.5 to the power of 10, 0.5 multiplied by 0.5, etc., etc. And we arrive at our likelihood. And you can already see that this figure is a lot tinier than the one that we saw with our previous model. And of course, we take the -2 log of that, and we arrive at the -2 log likelihood of the empty model, or the null model, which in this case is 13.86. So the difference between these two log likelihoods is what we call the log likelihood ratio. This likelihood ratio is approximately chi-square distributed under the null hypothesis, and it has degrees of freedom equal to the amount of parameters difference between the models. So in our case, because we only added BMI to our model, the difference between an empty model and our model with BMI is 1. So the amount of degrees of freedom that we have is 1. And of course, as you may know, we can use this chi-square distribution to determine if our model is statistically better than the previous model, in this case an empty model, which is just as good as flipping a coin. It's a 50-50% chance. So we can just subtract the two -2 log likelihoods, 13.56 minus 5.425, and we can find that that is statistically significant at the 0.05 alpha threshold. So, to conclude, we have determined that our model, including BMI, predicts the status of blood pressure a lot better than without BMI, which is not really surprising. Obviously, our model is a very, very simplified version of the reality, but it just goes to show that this model is better than a model without the variable BMI. We can also use the log likelihood ratio to determine if we can further improve our model. So, for instance, let's say that we would want to add another variable to the equation, say, for instance, whether somebody is physically active or not. We can then determine whether that actually increases the likelihood function or improves the likelihood function compared to a model in which we just had BMI. So we can use it to compare nested models, which is an assumption when we use this log likelihood ratio. So just like with linear regression, there are certain assumptions that we need to meet when we do logistic regression. So the first one, like with many statistical analyses, we need to have independent observations, indicating that observations should be independent from one another. One observation should not influence the value of another. Additionally, like with linear regression, we need to have a linear relationship between the independent variable and the log odds on the dependent variable. It's very important. And finally, we also have to have little to no collinearity between the predictors that we use in our model. So these assumptions, together with the further interpretation of the regression output in SPSS, will be a part of the next 2 videos. So hopefully see you there.